In this video, we are transitioning from forces into a new major topic in physics, which is energy. So we're going to see how that transition takes place with a term known as work, elaborate, expand on that with something called the WorkEnergy Theorem, and along the way we will slip in the terms energy as well as kinetic energy. So let's go ahead and get started. Part A, work and energy. The first bullet point says that when an object experiences a force over some distance, we say that work was done on that object. And I'm going to direct you to this diagram here. I have a person pushing on a box. Maybe originally the box was just sitting here on the surface, and then the person starts pushing on it with some force F, and the box slides along the ground a distance d. So the box experiences a force to the right. Some distance it travels is going to be labeled as d. All right. Since those two things occurred, there was a force and that object moved a distance, work was done on that object. Or sometimes put another way, this force did work because there was a force and it traveled a set distance. The equation for work, the actual way to compute the amount of this new term, is very straightforward. It's the force that's applied, F, times the distance the object travels, d, with one very important detail. Work always has to do with the force and the displacement, or the distance, that's parallel to one another. Here, the box is moving horizontally in the x direction. The force applied is in the x direction. So for this example, it's very valid to say the work here is F multiplied by d. But there are going to be times when the force and the distance traveled will not be perfectly parallel. And then, like we've done in the past, you might have to break things into components. What I mean by that, let's say this person, instead of pushing directly to the right, was actually applying a force this way, up and to the right. So let's say that was their force. Well, if we could measure that angle from right here, it's still going to be moving a horizontal distance. So we would want the horizontal component. We would want, let's see if I can squeeze this in, that piece right there, that's F times the cosine of theta. So you might see the equation written like this, F times d times the cosine of theta. Okay? To be honest, this is often how the equation for work is written, but I don't want you to get held up thinking it's always cosine of theta. This is the rule. You want the force and the distance that are parallel. Whether it's sine or cosine, however you're doing it, you want the two things that are in the same direction, okay, acting to the left or right in this case. Okay, now work is a scalar, like mass, like time. Okay, we are not going to have positives and negatives to indicate direction. However, work is a little weird. Work can be positive and it can be negative, but for different reasons than how we're used to using those two things. Work is positive if the force and the distance are in the same direction. For example, the force on the box is to the right, the distance is to the right. For this force here, the work should be positive. But imagine there was friction acting on the box. We know that friction always opposes motion. There's a frictional force there. Even if the box is still being pushed, if the box goes from left to right, friction is acting in the opposite direction. Well, then we would say that friction is doing negative work. Likewise, while the box is experiencing positive work by Newton's third law, we know, again, if I'm going to cross this off right now, if I'm going with this guy, if the person is applying a force to the right, the box is applying a force to the left. There might be negative work done on the person because they're still moving a distance d, but now their force is in the opposite direction. So this is weird. We're still going to have plus or minus, but for work, it's not because of direction. It's not because the box was moving to the left that it's negative. That's incorrect. The work might be negative if the applied force and the distance traveled are opposites. in opposite directions. Now, work has units. They should match the units for our equation. F is newtons, of course. Distance is in meters. So the unit for work is Newton meter, Nm. That's given its own special name, however. That's given the name of joules, but spelled a little weird, named after a guy, Joules, usually abbreviated as just uppercase J. All right, so work is measured in joules. Here is the first major definition of work. There's a second major definition. They're certainly related to each other. All right, and you'll actually see that later on. But work also corresponds to the change in an object's energy. Now, to be honest, I don't really want to give you a definition for energy. Physicists have kind of this weird roundabout definitions for work and energy. If you ask them what the definition of work is, it's something that causes a change in an object's energy. If you ask that same person what's the physics definition of energy, they'll say it's the ability to do work. That doesn't really jive with me. That doesn't really help me out. Energy is really, if you think of it, like a verb. Anything that has an ing ending, running, walking, falling, heating, expanding. All right, energy is the ability to do something, some verb. Now, that's not an official definition. I'm not going to write it down. You all had a working knowledge of energy before you walked into this class. But when work is done, the energy of an object changes. For example, this box. Imagine this box was just sitting here. It wasn't doing much of anything. It was just hanging out. But when you started applying a force, it started moving. There's that ing. It started having motion. Well, motion requires energy. So by doing work, by pushing on the box, by applying a force and a distance, the box started doing something. It gained energy. All right? Now, individual forces can do work, right? So I could look at the work done by this force here. I could look at the work done by the frictional force. I could look at the work being done on the person. All right? You could take that individual force, multiply it by the distance traveled, figure out the work by that specific force. You can also look at the net work. And if you want to look at the total, the net work on an object, you, which might not be surprising, would want to look at the net force. That's our transition into the next slide. Part B, the WorkEnergy Theorem and kinetic energy. All right, the work done by the net force. So now I'm specifically talking about the total work on an object. So the work done by the net force acting on an object is equal to that object's change in kinetic energy, a term you may not have seen until just now. Okay, here's the equation. This one to a lesser extent, but this is really the big one. I'm not going to spend time in this video talking through the derivation of this formula, how I got it. It's actually going to be the last slide on this video. You can hit pause and you could quickly skim over my just handwritten quick derivation. But knowing that work is equal to force times distance, you can derive this equation. The work is equal to 1/2 mv squared minus 1/2 mv naught squared. All right? If you put yourself in the shoes of a 17th century physicist in the era of Newton, if you derive this equation, it's not simply a boring regular derivation you're doing any day of the week. This is fascinating if you stumbled upon this derivation, because this is telling you something very major. When work is done, something, look at this, we have two very similar terms. Something, whatever these terms are, is changing. You're going from an initial amount to a final amount. This is the classic change. 1/2 mv squared minus 1/2 mv naught squared. One thing minus another. The difference, the change. This is where the term kinetic energy comes from. Someone didn't just, randomly pull out, oh, I'm going to create something called kinetic energy. I'm going to give it this equation. When physicists derive what's going on when there's a net work acting on an object, this term pops up. Something about the object changes. It seems pretty fundamental. It's the same term. They coined these terms kinetic energy because they're based on v, the speed or the velocity of an object. So when work is done, there's a change in kinetic energy. Kinetic energy, therefore, was just pulled from this equation, and it was defined as the energy an object has due to its speed. Again, just because, well, there's speed in that equation. All right? Certainly, we're going to be using the term speed and velocity pretty interchangeably. Technically, this is a velocity term, but even if velocity was negative, the term is getting squared. So any negative is going to get removed anyway. Kinetic energy is a scalar, so it doesn't really matter. There's no significance between using the word speed or velocity. Just like work, kinetic energy is a scalar, and like work, and in fact like all types of energy, the unit for kinetic energy is joules. So here's just the term kinetic energy all by itself. At one moment, the kinetic energy of an object is equal to 1/2 that object's mass times its velocity raised to the second power. When there's net work being done, the object experiences a change in energy. And this matches what was on the other slide. If you remember, something that's on the other slide is this. When there's work, there's a change in energy. Here's one example. There's a change in kinetic energy. All right? So we didn't officially write down a definition for energy because, frankly, there's not a great one. We did introduce work. We introduced the WorkEnergy Theorem. And then we looked at the kinetic energy term. All right, thanks for watching. I'm going to end with the very last slide, which is just going over the derivation, how we get the WorkEnergy Theorem right here. I'm not going to talk it over. You can hit pause if you want to read over it. Thank you for watching.